Have lovingly entitled The Heavenly Blanket. Perhaps you are yearning for a blanket right now to cuddle up with and take a nap. And so if you fall asleep, don't worry, it's okay. So we're going to talk about whether there is fine-tuning or design with carbon dioxide in Earth's atmosphere. So once again, I'm going to be looking for chemical evidence of design dealing with the amount of carbon dioxide in our air. Actually, the news media has made my argument for me, but I would like to add a few other things in addition to that. Just as a reminder, going back to how we made cookies, and we think about if you put too much, that's bad, and too little is bad as well. And see, look at people always, yeah. And so we want to remember that when we look for things. So we're going to do that with carbon dioxide. What if you had too much? What if you had too little? Are we in a nice sweet spot for life on our planet? So we're going to look at that. Now, this is a great question that I've been fascinated with. This is what you're breathing in: 78% nitrogen, 21% oxygen, roughly a percent of argon, 0.94, and then 0.04% carbon dioxide. So we are taught when you're growing up that you breathe in oxygen, but that's clearly an incomplete picture. And then, so what do you breathe out? So you're told you breathe in oxygen and you breathe out CO2, carbon dioxide. But that's not quite right. You see, when you breathe out, a little bit of the oxygen gets converted into carbon dioxide, and you go from about 21% oxygen, and there's still oxygen coming out of your mouth. You say, well, that's not what I learned in, I don't know, Carter, have you learned about that yet? So maybe 7th or 8th grade science class, that you breathe in oxygen and you breathe out carbon dioxide. Well, a little bit of it switches over. We're smart people. We should be able to think about this in a little more detail. In fact, you should know this because if you have a fire that's going out, you breathe on it, right? So if your breath was nothing but carbon dioxide, you would be putting the fire out. But yet it goes because you have still some oxygen. And in fact, if we were breathing out nothing but carbon dioxide, you would be at great risk for harm in this room. You're already at great risk for harm, perhaps, from other ways. But in fact, I thought about this. I thought, well, maybe this is why I fall asleep when I sit down in rooms, is because of the buildup of carbon dioxide. And when I worked at this place in Texas, where my wife and I met, in College Station, Texas, a company called Lintec, and I happened upon a carbon dioxide detector, and I thought, this is great. I'm going to take it to our Friday afternoon meetings. It was in a much smaller room. It was a lot like this, but very enclosed, no windows, and I would always fall asleep in there. And I thought that is because of the buildup of carbon dioxide, because I, too, as a PhD chemist, remembered what I was taught when I was younger. You breathe in oxygen and you breathe out nothing but carbon dioxide. So clearly the levels had to be going up in the room, and it was putting me to sleep, and I was going to prove it once and for all with a carbon dioxide detector that I brought to this Friday afternoon meeting. And so I brought it in, and sure enough, there were the levels, whatever they were, roughly around this. And then, man, I'm going to watch these levels just skyrocket as I fall asleep during this meeting. And then throughout the meeting, the numbers really never changed. And I thought, what's going on here? And I really actually never put it all together, or at least I thought, well, maybe there's a lot of mixing or something that's going on with regular fresh air that I wasn't aware of, which could be happening. But then when I think about it, we weren't actually putting out that much carbon dioxide as I once thought. So I was falling asleep for other reasons. Perhaps I was tired or too many carbs or something. So where do we find carbon dioxide? There is a lot of great fun places to find carbon dioxide. You can go to the store and find carbon dioxide as a solid. It's often sold at the front of the store in a cooler, and you can use solid carbon dioxide, and it's super cold, and you can use it to cool down your lunch or your supper or your basket picnic meal. And so people use it for a lot of things. But that is not, they call it dry ice because there's no water in it. So things that when there's no water, we call them dry. So you can have dry liquids because there's no water in them. Wet and dry refers to the amount of water that's in it. So we call it dry ice, super cold, and it would be fun to have some. I think last year I had some. We're going to do some other fun things. But I thought I'd show you these videos. These are some fun things you can do with dry ice. We would get it from our neighbors, and then, because the neighbors said, I don't know what to do with this dry ice, this carbon dioxide. Well, he just said dry ice. He didn't know what it was. And he said, I want to throw it into our pool. And my wife said, no way, that's a dangerous chemical. You can't throw that into the pool. And you can throw it into a pool. And it would just bubble. And so he gave it to us. And he said, oh, let's do something fun. And kids, you may remember this. So I just made a few little videos. Hopefully it'll work. Okay, so I put some dry ice and water in a plastic water bottle. And you may be able to see that it's getting a little bit fatter. And so the solids, as they become a gas here, expand to about 1,000 times their volume. And you can do fun things and slightly dangerous things like this. And I forget how long this one takes here. This one took a while. All right. You see it? Is it expanding at all? Oh, there it goes. There you go. So those guys can hold quite a bit of pressure until that just took a long time. There we go. Wow. Woo! Yeah, okay, there's a breaking point there. We found, I think I was doing this one here. This one is the Gatorade bottles, and we find that they blow out at the end. This is our driveway here. And then the weak point's in the end. So you can actually direct those. So those are kind of fun. All right, so we find carbon dioxide in a lot of places. There's dry ice, and you can do some dangerous things with that. You didn't learn that here, by the way. And you can find it in soda. This is what gives it its distinctive little, acidic but flavorful thing. So I don't know, kids, you guys want to come up? So we're going to do some fun things with soda. And one of the things is, should you ever shake a can of soda? Here's Carter. This was, Carter, can you recognize yourself? This was only a year and a half ago. You look so young. This was in March 2018. And so Carter was challenged with the thing that you're never told to do. Tell you not to do with the can. Okay, open it up. We do danger. Okay. Whoa, it's messy, right? Messy. Girls, you want to do this?
What does it taste like?
Yeah.
Is that great?
Okay. So we are going to do that here as well. So grab a can. And we're going to shake them. I'm going to try this one right here. All right, so we're going to shake these right here. You guys ever heard of what you can do if you ever encountered a shaken can to make it so it's not dangerous like that? Tap. Where do you tap? On the top. I think I did this at camp. You remember that? Yeah. Okay. Yeah.
I know this.
Yeah, exactly. All right, but I haven't done it with diet, so this is a bit of a danger here. All right, so you have. Oh, these are. How do they feel? Cool.
They're cold.
Oh,
no,
they're not that cold. So it doesn't work too well when it's cold, as we found out. All right, you've heard tap on the top. That doesn't really work well. What happens is the carbon dioxide bubbles, when you shake it, all go to the edge. And if you go around the edge right here, in theory, and in many practices, it doesn't explode on us. So we're going to go around twice here. Okay. I go around twice just to make sure all the bubbles are up there. Are you guys ready? If we make a mess, we'll just clean it up here. You guys ready?
Yes.
Okay. On the count of three, let's see what happens. 1, 2, and 3. See, this one, mine worked great.
Cold.
What's wrong with you guys?
They're cold.
They're cold. So, but it's not too bad. You got a little bit there. Oh, yours is just right on the top. Oh, can you fix that? There you guys go. You go share some with your sister. All right, go ahead. Yeah, okay. You refuse. You want one, Cadence? Just share with your sister. All right. You guys are about half the size of Carter, so. All right. So now I made a little mess. I'm going to clean that up. All right. So that's fun. The carbon dioxide, when you shake it, wants to come out because it's under high pressure. Now, another thing you can do with these things is, okay, we already did that one, is do the good old Coke and Mentos experiment. And this is a fun little video we saw, in case you don't know what the Coke and Mentos experiment is. Turn the volume up. How many people have done the Coke and Mentos thing? Oh, that's pretty good. It's actually kind of sad. You guys got to go do this. This is super fun. This is the best dollar you'd ever spend. Or maybe two, because you got to get the Mentos. Now, she created a little device to which she can put the cap on with a small hole in it. And then as she pulls the string, I actually created one like that.
3, 2, 1, go!
So the smaller the hole at the top, the higher that thing will spray. All right.
Oh, what an amazing thing! Hi, I'm Amita.
All right, so we're going to do that in here. And you can buy these little geyser tops here. Okay. Now this is going to be a little bit messy, don't you think? Yeah. All right, so you guys, everybody bring the mop. All right, so you can buy these little things. These are much better than what Emily Peppa had. It's a little release valve that you can pull and drop them. Ooh, oh man, that pulled right off. Okay, that's a little strong there. There we go. There, I think it was stuck. And so this will release the Mentos into here, and then you can get fun little tops with holes in them, or with star shapes, and you can get all sorts of spraying. And so this is a fun thing. Yeah, go ahead and load that up. That we can do here. See, I told you guys this was the splash zone. You didn't think I was going to actually, or I was joking there. It's for real. We're gonna do this inside. Are you ready, Carter? Okay. Let's get some of the stuff out of the way here. Okay. Do you think this is going to make a mess? Well, we need a special cap for that. Here, I got a special. I'll get this one right here. All right, so we're going to do this one inside. I'm going to get that one with a different way here. And make sure we got enough here. There. In fact, let's just do it inside of this one. All right. All right, so this is how you do this experiment inside. All right, make sure it's nice and tight. Let's go ahead and lift it into here. And don't, yeah. All right. There is some leaks in this system, but we go ahead and set that up. This is how you do the Coke and Mentos inside. You can get some PVC pipes. We saw some people doing this, so we thought we'd recreate it here. Not sure how clean these cups are. So now notice I am not using Coke. It doesn't matter. What do you think the key ingredient is in here? Carbon dioxide. So anything that's carbonated, this works. We've tried all sorts of candies. Mentos does work the best. And what do you think, Carter? Pretty good? Okay, I hope I didn't mess you up there. All right, you ready? Okay. 3, 2, 1, go for it. There's some leakage there. Okay, that one's not as great. But we got it there. And Carter, why don't you go and switch out the cup? Yeah, there you go. Okay. So you can try different sodas and different candies, and you can see that was okay. Don't do it with cold soda. It wants to hold on to the carbon dioxide and not release it as much. And so this doesn't. Okay. So that's how you do it inside. You guys thought I was going to make a big mess. All right, Carter, you want to hold that up? Hold that up. We're going to just so it doesn't tip over. Let's go over here and set it down. And there you go. All right, because we got some other things to put up there. All right, so that's some fun things you can do with carbon dioxide because we use it for all sorts of things. And you guys look like you want to drink that, don't you? Yeah. Yeah, go ahead and set that up. So we want to do some more things with carbon dioxide. And think about its application. So Carter's going to set up some other experiments that we're going to get to in just a little bit. So where do we find carbon dioxide besides sodas and and dry ice? Well, we find it in our air, and it comes off of anything that's burning. So any fire, volcano, gas emissions from combustion, there is carbon dioxide coming up. This is cars and any vehicle, airplanes, anything that's burning fuel is putting out carbon dioxide. You are burning fuel, so you are emitting carbon dioxide as well. So any living creature, animal, that is, produces carbon dioxide. Well, it turns out, as we understand plants and trees, they can also emit carbon dioxide during their night cycle. I was learning about this. But they typically, during the day, will bring in and take in carbon dioxide. So there's a nice relationship between plants and animals that we all know, but we should know that plants can actually emit carbon dioxide as well. So this is where we get a lot of it from our planet here. All right, so just a review on the amount that we're talking about in our air. We're talking about a tiny amount. So 78% of our air is nitrogen, 21% oxygen. That adds up to 99%. There's 1% left over. If you were to split that into another 100 bottles, 93 of those, or 94, would be argon. Man, there's a lot of argon in the air. And 4 of those would be carbon dioxide. And everything else that we know and love in our air, like pollutants and ozone and all that, are much smaller than this number here. Okay? So there is very, very, very little carbon dioxide in our air, and yet it does so much. All right. So this is what's been in the news since about the 1960s. Measurements have been taken near or in Hawaii, because this is out in the middle of the ocean where it would have little impact from people and activities that people would be doing. And so they've been measuring the amount of carbon dioxide in the air. And this is called the Keeling curve, and it has been going up as a general trend throughout the last few decades. And this is what has been attributed to the massive global warming and climate change that we're undergoing. So I'm not going to say too much about that. We're not going to talk about global warming, but we're not going to talk about whether it's a bad or good thing. I'm going to let you guys decide that. But we want to look at the design that's there. So 0.032% to 0.04% is what we're talking about this change. Percentage-wise, that's pretty small, but the impact on our Earth could be quite large. Now you'll see that these lines go up and down. That's because throughout the year it goes up and then it comes back down. I have a nice little video to show that NASA has put together on where that up and down comes from. Okay? So this appears to be similar to the amount of industrialization that's going on. And so this has been used to blame humans, and maybe rightfully so. This is still being debated in our world. So a little bit more about carbon dioxide. Carbon in the middle, 2 oxygens on the outside. It's colorless, odorless. It's actually a heavy gas. It likes to react with water to make carbonic acid, so we're going to do some things with this here so you can make sure you understand a little bit more about carbon dioxide. So we'll get into that. But let's talk about some of the dangers associated with carbon dioxide. You can actually have too much. And too much is related to hypercapnia. Too much. Capnia is the Latin word for carbon dioxide. That's related to that. And so there are some bad things that can happen if you get too much carbon dioxide. And I found it very interesting in the book, The Martian, page 230. We were talking about this on Monday. There's a quote in there that says, staying alive isn't about oxygen, it's about getting rid of CO2. The Martian is a story about, it's a fictional story about a man trapped on Mars, and his crew, he's left there by his crew because they thought he was dead. He wasn't dead. And then he has to live on Mars by himself for quite a while to see if he can get rescued or not. I will not ruin the story for you. But it is a fictional story. But they go into a lot of great chemistry, and I love it because it was a lot of the things that I like to talk about in these type of talks. And so they listed some of these things. 1% of carbon dioxide, you get drowsy. 2% is like being drunk. And then 5%, hard to stay conscious. And then 8% will kill you. And for a variety of reasons that take place inside your body that I don't even fully know or understand, but it's bad. So hypercapnia can have some really dangerous things on our body. Now, one of the greatest dangers that comes from carbon dioxide is illustrated with this natural event that took place many years ago. Carter, we're ready for you. You can go ahead and start with this one right here. So Carter is going to be doing an experiment while I tell this story. And so he's going to create carbon dioxide. You got the lighter? There's one right there. And he's going to light these candles. See, you and I, we're a lot like fires. We give off carbon dioxide, and we need the oxygen to live. So what we do, when we do experiments with fire, we're really doing them in simulation of what people are doing. So Carter's going to light these candles here, and he's going to create carbon dioxide with the classic baking soda and vinegar experiment. You can use any acid with baking soda, and it will create carbon dioxide, and lots of it. So he's going to create lots of it in this graduated cylinder that's very tall. And you got enough in there? Okay. You probably need something to scoop it with, don't you? I didn't bring a good spoon. Let's see what you can find in there. Just pour it in. We'll make a mess. We'll clean it up. All right. Okay, just pour what you can in there, a little bit in the bottom, and then he's going to add some vinegar to it to create the thing. I did bring glasses, though, so you should put some glasses on. How about here? I brought them. Did you get a lot in there? Okay, no problem. All right, it's pretty cheap. So here, you want the yellow glasses? Here. All right, we're going to try to remember safety, right? All right, very good. All right, so Carter's going to put this in here, and he's going to demonstrate one of the properties. Whoa, okay. All right, get ready to do your thing. So baking soda and vinegar. Go ahead. Okay, nicely done. See, when Paul did it, he put his hand in there. Yay, good job. All right, I'm going to keep him busy. You need help? Yeah, I'm going to carry it. Here. All right, so we're going to redo this experiment in another way right here. I'm sorry, I need to do it. Did you head it up here? Okay, let's get this down. All right, so let me tell the story now while he's getting that set up. Same thing. Now, there in Africa, there is a lake that's on top of a mountain, Lake Niles. Oh yes, don't forget to get them lit first. Yeah, I forget that sometimes. So you're doing good. All right, so he's going to light all these candles, and he's going to, over in these little bins here, he's going to make carbon dioxide. So I'm going to tell the story while he's doing this. So this lake is on top of a mountain. And underneath the lake is a dormant volcano, but it's like releasing a bunch of carbon dioxide. This lake, as you can tell, is very deep, so it's very heavy, and it was holding up carbon dioxide inside as like a big bubble underneath the lake. Well, so on top of this mountain with the lake, on the sides of the mountain, there was 3 villages. And the carbon dioxide was building up year after year with lots of carbon dioxide. But since it was on top of a mountain and was actually in a crater, the wind would go over it and it would never stir this lake. And so the carbon dioxide would continue to build up and build up. Well, eventually, there was a storm that happened that turned the lake over, and the carbon dioxide came out. And just like our little candle ladder here, the carbon dioxide came flowing down the side of the mountain and into the villages. And as you can read there, of course, what happened there, a lot of people were sleeping, and they were low to the ground, and carbon dioxide came over and settled over the village and suffocated thousands of people. 1,700 people in 3 different villages died. Now, there were people that were standing up, and they were they lived through the experience. But they could not see that this was coming because it's an invisible and it's an odorless gas. Now, you may smell some odors, but that's only from the vinegar. All right, so Carter is, we're recreating these situations here. And so what's happening is he's creating a lot of carbon dioxide, but it is a heavy gas. And so what's happening is that, yeah, keep pouring some in there. As he is adding the vinegar and he's going to create more carbon dioxide, it is heavy, and it's going to start to create a pool of it at the bottom, and you will see that as the oxygen is displaced, the candles will start to go out. So he's creating a lot. Now, I used to do this with the lid, with a lid on top to try to trap the carbon dioxide. But then I thought, well, people are going to say, well, if you have the lid on there, you're just eating up all the oxygen, and that's why it's going out. And so we're not doing that here. Man, those candles are taking a while there. Yeah, I think it's fine. Just keep, it'll go. It'll go. We got to trust it. We got to trust it's going to happen. How many times have we done this? A lot, haven't we? Yeah, so just keep pouring some more in there. It might make a little bit of a mess. So we keep it open to really, there you go. Woo. So that pushed a lot of it that way. Yay! More to clean up, right? Okay, now notice the really short ones have gone up. So okay, so it's working. It just took a little bit to build up. So imagine that carbon dioxide is building, it's heavy, it's building up at the bottom, and it is starting to come up here. And so these short candles have gone out, and it's just taking a little while to build up. Now we can't blame it on the oxygen getting used up because they can still take the oxygen from the top here. So we're not going to move our hands over the top too much. We're just going to keep adding some more carbon dioxide and just keep it going. And so carbon dioxide is actually a very, very dangerous gas for this reason right here. It is heavy, and it will displace oxygen, and then you cannot live. Now, we can see where that level is now because those shorter candles, that one's up, there it's out, it's building up and building up and building up. If we have too much carbon dioxide around, it will displace the oxygen that's there, pushing the oxygen up and away from the surface. There you go. He's got all of them out. We're just using the heavy properties of carbon dioxide to put those candles out. Carter, go ahead and see if you can relight those candles and see if that can work there. All right, there we go. And all right, come on, Carter. You know how to use this thing. Now, why can't he light that? The carbon dioxide's in the way. I can tell him all day long, and he won't be able to do it. Okay? There's just too much carbon dioxide. Good try. Good try. All right, good job. Thank you. Another hand. Oh, me, huh? Yay! Yeah. So it's really cool because you can then see where the level is of the carbon dioxide by taking it down slowly. And so there it's at. All right. All right, we'll get to that in just a minute. Thank you, sir. We'll be ready for that. All right, so we've got another one coming up very soon here. So very dangerous. So in these lakes, there's a couple of them. What they have done now is put tubes down to the bottom to have a release pathway for carbon dioxide, so this will not happen again. Okay? So if you're interested, there are actual numbers to the density of carbon dioxide relative to other gases that we know and love in our air. So it is roughly around 2 grams per liter, and that's heavier than oxygen and nitrogen, the main components. And so it displaces that out. Now, interesting thing that I want to put into your head is ozone is even heavier than carbon dioxide. Where do we find ozone? Up in the upper atmosphere. Wait a second. How does that heavy gas stay up there? Is there a bunch of people holding it up? How does it stay up there? And so that'll be the subject of the talk, and maybe in a couple times. I think next time we're going to try to talk about water next time. So it just so happens that we have our 2 main ingredients have a really nice match in density, and this carbon dioxide, which we have so little of, is heavy, but we have so little. So imagine, if you would, if we did have a lot of carbon dioxide, what could happen is that valleys could fill up with carbon dioxide and argon, because argon is heavy as well. And it would push the oxygen up. We do not have this problem on our planet. We can go to valleys, and it's no problem. We can go into basements, and it's no problem. There's other dangers dealing with gases, but not from carbon dioxide. Why? There's so little of it, and it's moving around. And I'll show you a picture in just a second. So actually, scientists use this to create oxygen-free atmospheres. If we want to do an experiment without oxygen, we flood the system with carbon dioxide or argon, and that will get rid of the oxygen. Okay? But that's not a problem for us. And one of the main reasons why it's not a problem is there's so little is because it moves.
Hi, this is Bill Putman. I'm a climate scientist at NASA's Goddard Space Flight Center. What you're looking at is a supercomputer model of carbon dioxide levels in the Earth's atmosphere. The visualization compresses 1 year of data into a few minutes. Carbon dioxide is the most important greenhouse gas affected by human activity. About half of the carbon dioxide emitted from fossil fuel combustion remains in the atmosphere, while the other half is absorbed by natural land and ocean reservoirs. In the northern hemisphere, we see the highest concentrations are focused around major emission sources over North America, Europe, and Asia. Notice how the gas doesn't stay in one place. The dispersion of carbon dioxide is controlled by the large-scale weather patterns within the global circulation. During spring and summer in the Northern Hemisphere, plants absorb a substantial amount of carbon dioxide through photosynthesis, thus removing some of the gas from the atmosphere. We see this change in the model as the red and purple colors start to fade. Meanwhile, in the southern hemisphere, we see the release of another pollutant, carbon monoxide. This is a gas that's both harmful to the environment and to humans. During the summer months, plumes of carbon monoxide stream from fires in Africa, South America, and Australia, contributing to high concentrations in the atmosphere. Notice how these emissions are also transported by winds to other parts of the world. As summer transitions to fall and plant photosynthesis decreases, carbon dioxide begins to accumulate in the atmosphere. Although this change is expected, we're seeing higher concentrations of carbon dioxide accumulate in the atmosphere each year. This is contributing to the long-term trend of rising global temperatures. The Orbiting Carbon Observatory 2, or OCO2, will be the first NASA satellite mission to provide a global view of carbon dioxide. OCO2 observations and atmospheric models like GEOS-5 will work closely together to better understand both human emissions and natural fluxes of carbon dioxide. This will help guide climate models toward more reliable predictions of future conditions across the globe.
All right, isn't it really cool to see how CO2 moves around, how important it is to have moving air. That keeps that CO2 moving, keeps the oxygen coming back in. There's so little of it, and so it can easily move around. So the greenhouse effect is happening by carbon dioxide and other gases. And so what happens is light comes in, it traps the infrared, CO2 and other gases trap the infrared energy, thus warming it. You see, it's not just our distance from the sun that keeps us at our warmth that we have. If we didn't have these greenhouse gases, it would be Celsius. That's cold. It would be freezing. We would be an ice cube, a snowball, if we did not have greenhouse gases. Greenhouse gases are not bad. Too much of them can be bad. Too little is bad. We need to have the right amount. This is why I call it the heavenly blanket. Carbon dioxide is keeping us warm. We need it. It's not that we don't need any of it. We need the right amount. If we had other gases that were global warming gases, we would overheat. And this is what's happened to Venus, because it's 96% carbon dioxide. So it's actually hotter than Mercury, which is closer to the sun, but because it has greenhouse gases on it, Venus is much warmer. Okay, nitrogen, not a greenhouse gas. Oxygen, not a greenhouse gas. Argon, not a greenhouse gas. Molecules that have 3 atoms or more in it are all greenhouse gases. It's pretty easy to figure out which ones are and which ones are not. But is the blanket too thick? That's what we're worried about. In an analysis of the greenhouse gases, it turns out water is actually a bigger contributor to the greenhouse effect than even carbon dioxide. Water is a much better greenhouse gas, or contributes more to the overall greenhouse effect. Methane is more powerful as a greenhouse gas, but there's less of it. But it has a sizable contribution. People are making more and more of an issue of that as well. We need to be careful about the amount of methane that's being released in the atmosphere. Ozone is another greenhouse gas. And so these gases, plus other ones, combine to keep our planet warm. So it isn't just carbon dioxide. The blanket is actually quilted. It's made of many other different gases. But water is the biggest contributor to greenhouse effect. It's not carbon dioxide. which is why in that video he said carbon dioxide is the biggest greenhouse gas affected by human emissions. It's so hard to model this because water vapor is always going up and it's going down. You get clouds, you don't have clouds. This is a very challenging activity and to figure out. And so this is why I kind of reserved some judgment on what we're doing, because we really need to learn more about how this world works. All right, so I'm going to diverge into a little topic that I like to call what is natural. And we're going to do this experiment for that. You see, we look at this factory right here. Is this a natural? Is this something that naturally happens right here? Right? Chemical engineers are going, no, that's my job in the future. I'm going to make lots of money there. No one would ever claim that this system right here is natural. However, we do look around us and we see the word natural being used prolifically. In fact, it is used as a great selling tool. You put all natural on your product, you will probably sell more. Most places I go, if I ask people what's a chemical or what's all natural, we would say all natural means all good, and chemicals mean dangerous things. And we need to not think that way, because this is not the way it works. Okay, all natural doesn't mean all good for you, and I can easily prove that to you with the following picture. So what does natural mean? I mean, really, they're trying to get you to think that it means buy this because it's good for you. I understand that, but not everything from nature is good for you. I don't know if you guys can recognize some of these plants. They're all natural. They are found in nature. I would say God created all of them. Does anybody know what plant A is? Oh, you guys are so good. Anybody know? Those are tobacco leaves. All natural. All 100% all natural. Okay? Does anybody know what B is? Yeah, leaves of 3, let them be. All right? Poison ivy, 100% all natural. Anybody know what C is? Oh, well, okay, we see where it's all going now. 100% all natural. Anybody know what D is? Pokeberries. Yeah, they're not good for you either. I like this one down here. Anybody know what E is? What's that? Very good. Do you know what hogweed does? What does it do? You can get some serious rashes. In fact, what it does, when you get a little bit of the oils on your skin, it makes your skin basically transparent to UV light, which makes you very susceptible to getting third-degree burns just from walking outside. All natural, 100% all natural. Okay? The betel nuts, the Carolina Reaper, poppies, hemlock, 100% all natural. We are misusing this word, and it is causing great confusion in our society because we do not know how to use this word. And this is only the fun way that we're getting confused by it. There are lots of poisonous plants. In fact, my wife, I got her a nice book. What was that book called?
Wicked Plants.
Wicked Plants. And it goes through some pretty amazing wicked plants and how dangerous they really can be. All natural is not what you think it is. In fact, in many ways, it's not what you think it is. Let me describe to you what all natural, I think, should be defined and means. Carter and I are going to do an all natural chemical reaction. All right. Well, hang on a second. So we have. Hopefully this is distilled water. I can't remember if we traded it out. This is distilled water, I hope, and I'm going to put in some phenolphthalein, and the chemistry students should know what phenolphthalein does. And so I've just put distilled water with some phenolphthalein, and I'm going to put a couple of drops of sodium hydroxide in here, a base. And 1, 2, 3, okay? And phenolphthalein turns pink under basic conditions. So I've changed the pH with just a couple of drops of this. Okay, good. It's working like I hoped. All right. So now we're going to change this water by putting carbon dioxide into it. So this is my homemade carbon dioxide thing. All right, here. Sorry. Go ahead. Oh, is that the right side? Yeah. Go ahead and put it in, and I can go and close it. A lot of vinegar over here. You spill all that in. Man. Yeah, okay. Yeah. We're not making a mess. We're not. Oh man, except for I have an open wound. Okay. I'm getting some on my fingers. All right. So we're making our own carbonated water. Go ahead and mix that here. Okay. And we're just putting a lot of carbon dioxide into the water and on top of it, and it's pushing carbon dioxide in there. We need to wipe that up. Yeah. Your hands burning? Okay. You want to wash it off? There's some water. Okay. It's going to exfoliate your skin there. All right, you can use one of those. All right, so this is a fun way to carbonate. You just need a couple of 2 liters that you use from the Mentos and Coke experiment. Put the labels off. So we got lots of uses for covering these 2 liters in carbon dioxide. And so baking soda and vinegar. We put the baking soda in a Kleenex so that'll give us like a little time release so we can close it. You don't want it. Yeah. What's that? Yeah. Okay. Now there is a way that you're supposed to open this, and it's on this side right here. But you can go home and figure that out. Okay, because it will ruin it if you do it the other way. All right. So I think we're doing pretty good. Oh yeah. So the carbon dioxide changes water, and a way to make carbonic acid, which is very important. Okay, so go ahead and open it up. Yeah, the one that says open first. We have notes to ourselves. Okay. Now I'm going to take about the same amount of water and go ahead and let go. Okay, and I'm going to put it in here. This is carbonated water that has carbonic acid in it, and so it'll do some nice, interesting things here for us. And you can put the lid back on. Put some phenolphthalein in here. Okay, and 1, 2, 3 sounds good. Maybe 4, that doesn't matter. And now I'm going to put some sodium hydroxide in here, and let's see if something happens. 1, 2, 3. The color is not changing. 4, 5, 6, 7, 8, 9, 10. And the pH is not changing. Well, mainly because I did make an acid. But what's happening is this system has created a buffer. I can start putting a lot more sodium hydroxide in there, and the pH doesn't change. Okay? Carbon dioxide changes water and creates a buffering system. It does lower the pH, but when it's exposed to a base like this, you guys will learn in general chemistry, I'm creating a buffer system. And this buffer system is what keeps the pH from changing in our oceans and in our bodies. Okay? So this is a very important thing. So carbon dioxide provides the tools, the chemical tools, to make a pH buffer system that protects all of our waters from changing the pH. Carter, thank you very much again. You can have a seat. All right? And so I would say this is natural. When carbon dioxide mixes with water, it naturally, spontaneously is the key word, makes carbonic acid. Okay? Well, what about if I take carbon dioxide and water, now the same 2 ingredients, and I add light to them? Can I naturally make sugar and oxygen? Is it just need light? Could I take this exact same thing, shine light on it, and have photosynthesis take place? Is this a natural thing that can take place? Am I just missing some light here? Okay? This is our great question. Because this is happening in nature right now. Right? This is what's keeping us alive, because it's producing carbon dioxide, or making oxygen, and is creating food for us. All right. In the interest of time, there's a great video. Most of you know about photosynthesis. So I'm going to jump to a few other slides to wrap up some of this here. There's 3 simple ingredients that come together to make glucose and oxygen. It's a fun video to watch. All right, what is taking place? Well, light is being captured by chlorophyll that is in plants. In my graduate work, when I was in graduate school, I worked with molecules that were very similar to chlorophyll. Here's chlorophyll. I worked with some of these, I call chlorphrin. I was able to learn how to connect things to them and how light is absorbed and electrons moved in a system very similar to photosynthesis. So I'm going to say I don't know everything about photosynthesis, but I do know how to connect molecules together to move electrons around, and that's what's happening in photosynthesis. I built it with 3 molecules, and it took me a few years to prove that I made that and to get the effect that I wanted. And so I'm going to jump over this for a second. Inside of the plant in photosystem 1, there are, how many? There are, I thought I was supposed to jump up here, over hundreds of different molecules that are precisely arranged to capture light and create the electron arrangement that's needed. These systems are very fragile and are easily broken. I think this was a list from this book here. This is a good book. Oh, here it is. 288 chlorophyll, 66 beta carotenes, 9 lipids, some vitamin K in there, and a bunch of other little parts in there. There are over 300 to 400 parts that have all come together simultaneously to capture light and create chemical energy. Photosystem 2, which is right next to that, has 99, 20, there's well over 100 little chemical parts that have come together to make the photosystem 2 that plays a part in creating photosynthesis. So when we read things like 3 billion years ago our world changed, life on Earth relied on limited natural resources, blah, 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 everything changed when tiny cells discovered a way to capture light and power their internal processes. The discovery of photosynthesis opened up vast possibilities of growth. Well, discovering it is really quite a challenge because even with lots of scientists, putting just 3 or 4 parts together is a huge challenge. There are hundreds and hundreds of pieces that have come together to create photosynthesis. We are misled because chemistry is too hard for everyone to understand that it's not just 3 simple ingredients. There are thousands of specifically arranged parts that have come together to create and change the products of carbon dioxide reacting with water. This is about as unnatural as you can get. You see, someone designed a system with all of these parts. Now, they've automated this design, so it seems easy to do. But to make dioxygen gas is actually extremely challenging, and I would wager the word unnatural. In fact, we do not see any other planet with oxygen because the only way to make oxygen is from plants. And plants, I'm going to argue, are not natural. Okay? They are it's a conglomeration of chemical systems that are very hard to put together to do anything useful. In fact, it's one of the biggest mysteries that people have pointed to. Where did our oxygen come from? How did these plants really get started? You see, when we look at a plant, we should not see a natural, easy-to-make system. You should be seeing an unnatural design system that is similar to a chemical factory. In fact, these are the words that textbooks and other scientists are using when we look at plants. So when we see this, this is not natural right here. Plants are unnatural. Plants are utilizing and doing unnatural chemistry here to create and sustain life here on this planet. And so I'm going to jump to some of my last slides here because you guys need to go. And I would love to unravel this more with you. But when we see systems that look like this that are unbalanced, we go, somebody built this. Okay? When we look at this, we go, somebody built this. But we look at this, we go, nobody built this. This happened by chance. There are 1,000 more pieces than there is in this. But when we look at this, we go, nobody made that. We need to change the way we talk about the words natural and chemical reactions so that we can understand that we're not living in a natural world. We're living in a supernatural place that's been designed. So I try to lay out some of those things for you today. I hope you appreciated that. If you could turn in your piece of paper to me, that would be great. And sign out. Thanks for coming. We're going to talk about water next week.